When we think about stars, we think about certainty, about objects whose behavior is so well understood that we use them to measure distance, age, and time across the universe. Their light rises and falls in patterns we can predict. Their lives follow rules written long before we ever observed them. But there is a more unsettling possibility. What if a star doesn't simply evolve, explode, or fade, but behaves in a way our models cannot fully explain? What if its light vanishes not gradually, but abruptly and irregularly, as if something is interfering in ways we don't yet understand? In recent years, astronomers began paying attention to a star in our own galaxy that dimmed by extraordinary amounts, losing up to 20% of its brightness without any consistent rhythm. Not once, but repeatedly. Not in ways that matched planets, dust, or stellar aging. A phenomenon first dismissed as error, then as coincidence, and finally as something that refused to go away. Tonight, we're not claiming we've discovered something exotic or extraordinary. We're asking something more careful and more unsettling. What happens when a star violates the assumptions that underpin modern astrophysics? And if we cannot explain its behavior, what does that say about the limits of what we think we understand? Before we go any further, if you value calm, grounded explorations of cosmic mysteries that treat uncertainty with restraint, a like or subscribe helps support this work. Because sometimes the most disturbing discoveries aren't the ones that rewrite physics overnight, but the ones that quietly show us how incomplete our explanations still are. Across the universe, stars are among the most predictable objects we know. Despite their immense power and scale, they follow patterns that physicists have studied for decades. Their brightness changes in ways that can usually be modeled, their lifetimes unfold along recognizable paths, and their behavior fits within mathematical frameworks that describe how matter and energy interact on cosmic scales. This predictability is not a trivial detail. It is one of the foundations of modern astronomy. By observing how stars shine, pulse, and fade, scientists can measure distances across galaxies, estimate the age of stellar populations, and reconstruct the history of the universe itself. Much of what we know about cosmic structure depends on the assumption that stars obey consistent physical laws. There are stars that vary in brightness, but their variability is rarely mysterious. Cepheid variables pulse in regular rhythms that act like cosmic clocks. Eclipsing binary systems dim with precise periodicity as one star passes in front of another. Even violent stellar flares driven by magnetic activity follow physical processes that can be understood and predicted. Across billions of stars, these patterns repeat with remarkable consistency. When stars reach the end of their lives, they do so in ways science has learned to anticipate. Massive stars explode in supernovae, scattering heavy elements across space. Smaller stars expand, cool, and gradually fade. Over cosmic time, these cycles repeat with such reliability that stars have become symbols of stability in an otherwise dynamic universe. But stability in appearance does not mean simplicity in reality. Beneath the equations lies a complex interplay of gravity, nuclear fusion, turbulence, and magnetic fields, all interacting in ways that are often hidden from direct observation. Most of the time, this complexity averages out into behavior that looks orderly and predictable. And then, occasionally, it doesn't. When a star deviates sharply from these expectations, it is not merely an anomaly. It is a rupture in one of the most stable assumptions in astrophysics. It forces scientists to question whether their models are incomplete, whether their classifications are fragile, and whether the universe may be capable of behaviors that do not fit comfortably within established frameworks. This is why the discovery of an unusual star matters, not because it is rare, but because it suggests that the rules we rely on may not be as universal as we believed. The anomaly did not announce itself with a dramatic explosion or a sudden burst of energy. Instead, it emerged quietly, buried within the enormous stream of data collected by NASA's Kepler Space Telescope. Kepler was designed to hunt for exoplanets by detecting tiny dips in starlight as planets passed in front of their host stars. Over its mission, It monitored hundreds of thousands of stars, producing a dataset so vast that most of it could only be analyzed with automated algorithms. Among these countless stars was one that initially seemed unremarkable. It sat in the constellation Cygnus, shining steadily like millions of others. But when astronomers examined its light curve more closely, they noticed something that did not fit any familiar pattern. The star's brightness did not dip gently, as it would if a planet were passing in front of it. Instead, it dropped abruptly, sometimes by more than 20%, an extraordinary amount for a main sequence star. These dips were irregular in timing, depth, and shape. Some lasted hours, others stretched across days or weeks. Some were sharp and sudden, while others faded slowly, as if whatever was blocking the light was diffuse and shifting. No known planet could produce such extreme and erratic dimming. No binary star system matched the observed behavior. The patterns were too chaotic to be explained by standard stellar variability, yet too structured to be dismissed as noise. At first, the discovery seemed like a curiosity, a strange data artifact waiting to be resolved. But as independent teams confirmed the observations and ruled out instrumental errors, curiosity began to turn into unease. This was not just an unusual star, it was something fundamentally different. Confronted with a mystery, scientists did what they always do. They searched for natural explanations. The universe is vast and strange, but history has shown that extraordinary phenomena almost always have ordinary causes, once they are understood deeply enough. One of the earliest hypotheses involved clouds of dust drifting between Earth and the star. Dust can absorb and scatter light, causing stars to dim in irregular ways. But dust has a signature. When it absorbs starlight, it heats up and re-emits energy in the infrared. Yet observations of this star revealed far less infrared radiation than such massive dust clouds would require. Another idea focused on comets. A swarm of comets passing in front of the star could, in theory, produce irregular dips in brightness. But to match the observed dimming, the swarm would need to be unimaginably large, far beyond anything ever seen in a stellar system. The scale of the required cometary debris pushed the explanation to the edge of plausibility. Some researchers suggested a catastrophic collision between planets or asteroids, generating a cloud of debris that temporarily blocked the star's light. But collisions produce patterns that gradually smooth out over time. The star's behavior, by contrast, seemed to evolve in complex and unpredictable ways, as if the obscuring material were constantly changing shape. Each hypothesis solved one piece of the puzzle while breaking another. Every explanation felt close but never complete. In science, incomplete answers are more unsettling than mysteries themselves. A mystery implies ignorance. An incomplete explanation implies that something deeper is being missed. And as the list of conventional explanations began to shrink, the question grew harder to avoid. What if the cause was not natural at all? At some point in every scientific mystery, there is a moment when the conversation shifts. The familiar explanations have been tested, stretched, and slowly exhausted. What remains is a gap in understanding that refuses to close. It is in that gap that dangerous ideas begin to appear. In the case of this star, one such idea emerged quietly, almost hesitantly, in academic discussions and online forums. It was not presented as a serious conclusion, but as a thought experiment, a possibility raised not because it was likely, but because it was difficult to rule out completely. What if the dimming was not caused by dust, comets, or debris? What if it was caused by something built? The concept was not new. Physicists had long speculated about hypothetical structures that advanced civilizations might construct around stars to harvest their energy. These structures, often referred to as Dyson swarms, were not solid shells but vast clouds of satellites or collectors orbiting a star, gradually capturing a significant fraction of its output. In theory, such a swarm could produce irregular and complex patterns of dimming, depending on its density, distribution, and motion. Unlike planets, it would not move in neat periodic orbits. Unlike dust, It would not produce predictable thermal signatures. It would behave less like a natural phenomenon and more like an engineered system. Most astronomers dismissed the idea almost immediately, not because it violated physics, but because of what it implied. To accept even the possibility of artificial structures around a distant star was to open a door that science had spent decades carefully avoiding. Yet the idea lingered, not as an answer, but as a shadow. Science is often portrayed as fearless, but in reality it is deeply conservative. Its strength lies in skepticism, in the refusal to accept extraordinary claims without overwhelming evidence. This caution is not weakness, it is the reason scientific knowledge remains reliable. But caution also has a psychological dimension. If the dimming of this star were caused by an artificial structure, it would mean that civilizations can reach scales far beyond anything humanity has achieved or even seriously imagined. It would suggest that technology can reshape stellar environments, that energy can be harvested on astronomical scales, and that intelligence may not be confined to planets, but extended into the architecture of stars themselves. Such a realization would not merely expand our understanding of the universe, it would destabilize it. Humanity has long comforted itself with the idea that advanced civilizations, if they exist at all, are rare, short-lived, or technologically limited. The absence of clear evidence has allowed us to imagine ourselves near the top of the cosmic hierarchy, but a single confirmed megastructure would shatter that illusion instantly. This is why scientists reacted with caution rather than excitement. They returned to data, refined their models, and searched for subtle natural explanations that could preserve the existing framework of astrophysics. Not because the extraordinary explanation was impossible, but because it was too consequential to accept lightly. As observations continued, the mystery refused to resolve itself. Instead of converging toward a single explanation, the data began to fragment into contradictions. Long-term monitoring revealed that the star's brightness was changing not only in sudden dips, but also in gradual trends. Over the course of years, its baseline luminosity appeared to drift downward, as if the star itself was slowly fading. Yet this fading did not match the behavior of aging stars, which change over timescales of millions or billions of years, not decades. At the same time, short-term dimming events continued to occur with no obvious periodicity. Some dips were sharp and brief, others broad and shallow. The patterns seemed neither random nor orderly, but something in between, a complexity that resisted simple categorization. Some multi-wavelength observations added further confusion. Different colors of light dimmed by different amounts, suggesting that the obscuring material was not uniform. Radio, optical, and infrared data painted conflicting pictures, each hinting at a different underlying mechanism. The more instruments observed the star, the less coherent the story became. It was no longer possible to describe the phenomenon as a single anomaly. Instead, it began to resemble a system, an evolving dynamic configuration whose behavior could not be reduced to one cause. In astronomy, systems are usually governed by physical laws that, once understood, reveal elegant simplicity beneath apparent complexity. But in this case, elegance refused to appear. The star did not behave like an object, it behaved like a process. And processes, unlike objects, often imply agency, interaction, or design. No one wanted to say that out loud. As the debate over Tabby's star continued, one truth became increasingly difficult to ignore. Whether the explanation was natural or artificial, the star had already accomplished something profound. It had exposed the limits of our understanding. Modern astrophysics is built on patterns. By studying millions of stars, scientists have learned to classify, predict, and model stellar behavior with extraordinary precision. The universe, when viewed statistically, appears remarkably consistent. Outliers exist, but they are usually absorbed into broader theories, explained away as rare variations of known processes. Tabby's star refused to be absorbed. Even if every proposed explanation turned out to be natural, The star still represented a category of behavior that did not fit neatly into existing frameworks. It was not just unusual, it was structurally inconvenient. It forced scientists to confront the possibility that their models were not as complete as they believed. In science, revolutions rarely begin with answers. They begin with questions that refuse to disappear. Every major shift in our understanding of the universe, from heliocentrism to relativity to quantum mechanics, started as an anomaly that seemed too strange to take seriously. Someone at some point had to decide that the anomaly was not noise but signal. Tabby's star sits uncomfortably in that tradition. It is a reminder that the universe is not obligated to behave in ways that match our expectations, and when it doesn't, the consequences can extend far beyond a single star. If one star can behave in ways we do not understand, the natural question is whether it is truly unique. Astronomers have observed hundreds of billions of stars in our galaxy alone, yet our detailed measurements cover only a tiny fraction of them. Most stars are too distant, too faint, or too poorly monitored for subtle anomalies to be detected. It is entirely possible that Tabby's star is not an exception, but merely the first example we happen to notice. This possibility is deeply unsettling. If strange stellar behavior is common rather than rare, it would suggest that the universe is far more dynamic and unpredictable than our models imply. It would mean that hidden processes, natural or otherwise, may be shaping stellar systems in ways we have not yet learned to recognize. The idea becomes even more provocative when viewed through the lens of cosmic engineering. Advanced civilizations, if they exist, would not necessarily announce themselves with dramatic signals or interstellar messages. They might instead alter their environments quietly, leaving behind signatures that resemble natural phenomena. A dimming star would not look like a declaration of presence. It would look like astrophysics. In that sense, Tabby's star is disturbing not because it proves anything extraordinary, but because it demonstrates how easily extraordinary things could hide in plain sight. If subtle modifications can masquerade as natural variability, then the night sky we observe may already be shaped by processes we do not yet recognize as artificial. The universe might not be silent. It might simply be speaking in a language we have not learned to interpret. Humanity has always imagined itself as an observer of the universe, standing apart from the cosmic drama and watching it unfold from a safe distance. We study stars as if they were distant objects governed by impersonal laws, untouched by intention or purpose. But Tabby's star invites a more uncomfortable perspective. What if we are not merely observers? What if we inhabit a universe that has already been influenced, altered, or reshaped by forces beyond our understanding, whether natural, technological, or something in between? In that scenario, anomalies are not just curiosities, they are clues. The history of science teaches us that the most important discoveries often come from phenomena that do not fit established categories. The expansion of the universe, the existence of dark matter, the acceleration driven by dark energy, each began as a discrepancy between expectation and observation. Tabby's star belongs to that lineage of disruptions. It suggests that our cosmic environment may be more complex than we are prepared to admit. Not necessarily hostile, not necessarily inhabited, but layered with processes and structures that exceed the explanatory power of our current theories. In that light, our position in the cosmos begins to look less secure. We are not standing at the center of a well-understood universe. We are navigating the edges of a system whose rules we only partially grasp. And if even the stars, the most stable and predictable objects we know, can behave in ways that defy explanation, then the foundations of our cosmic worldview may be far more fragile than we like to believe. Tabby's star does not prove that we are not alone, but it does prove something equally unsettling. We are not as certain as we thought. As the mystery of Tabby's star deepened, it began to connect with a broader pattern in modern cosmology. Over the past century, astronomers have discovered that the universe is not as simple or as stable as it once seemed. Dark matter bends gravity in ways we cannot see. Dark energy accelerates cosmic expansion for reasons we cannot explain. Vast voids stretch across billions of light years, while colossal structures challenge the limits of what theory says should exist. Tabby Star fits uncomfortably into this landscape of anomalies. Each of these discoveries began as a small inconsistency, a measurement that did not match expectation, a signal that refused to fit existing models. At first, such inconsistencies were dismissed as errors. Then they accumulated. Eventually, they forced physicists to rewrite their understanding of reality. In that sense, Tabby Star is not an isolated curiosity. It is part of a larger story, the gradual realization that the universe is governed by forces and processes we do not yet fully comprehend. If stars can behave unpredictably, if cosmic expansion can accelerate against all expectations, if massive structures can form where they should not, then the possibility emerges that our current models are not wrong, but incomplete. The universe may not be chaotic, but it may be operating according to rules that we have only partially uncovered. The unsettling implication is not that the cosmos is irrational, but that it is more complex than we imagined. And complexity, when viewed from a limited perspective, can look disturbingly like intention. One of the most enduring questions in astronomy is why the universe appears so quiet. If advanced civilizations exist, why do we not see clear evidence of them? Why does the sky seem devoid of unmistakable signs of technological activity? Tabby Star suggests a possible answer that is both subtle and disturbing. Perhaps advanced civilizations do not announce themselves with grand signals or dramatic interventions. Perhaps their influence is quiet, distributed, and indistinguishable from natural processes. Instead of broadcasting messages, they might reshape environments, alter stellar systems, or manipulate energy flows in ways that blend seamlessly into the cosmic background. In such a universe, the absence of obvious evidence would not indicate absence of activity. It would indicate sophistication. A dimming star would not be recognized as a signal. It would be catalogued as an anomaly. A strange light curve would not provoke alarm. It would inspire papers, debates, and incremental revisions to existing theories. Over time, the extraordinary would be normalized, absorbed into the language of astrophysics, and stripped of its implications. The night sky would remain silent, not because nothing is happening, but because everything is happening in ways that appear natural. From this perspective, Tabby Star becomes more than a scientific puzzle. It becomes a metaphor for our relationship with the cosmos. We search for dramatic signs of other intelligences, while potentially overlooking subtle evidence hidden within phenomena we are already observing. If the universe is being shaped by processes beyond our understanding, we may be surrounded by clues we do not yet recognize as clues. And silence, in that context, may not be emptiness. It may be camouflage. In the end, Tabby Star does not give us a clear answer. It does not confirm the existence of alien megastructures, nor does it completely dismantle our understanding of stellar physics. Instead, it occupies a far more uncomfortable space between certainty and mystery, where explanations exist, but none feel fully satisfying. Most likely, its strange behavior will eventually be traced to natural processes that we have not yet fully understood. History suggests that many cosmic mysteries, once thought impossible, ultimately find explanations within the laws of physics. Dust, debris, magnetic activity, or subtle stellar mechanisms may one day account for the star's irregular dimming in ways that seem obvious in hindsight. Science has a long tradition of turning anomalies into knowledge. Yet even if that happens, the deeper significance of Tabby Star will remain. Its existence reminds us that the universe is not obligated to behave in ways that align with our expectations or our models. Beneath the apparent order of cosmic systems lies a layer of complexity that we are only beginning to perceive, and every anomaly is a hint that our understanding is provisional rather than complete. Somewhere in the Milky Way, Tabby Star continues to change. Its light still fluctuates in patterns that resist simple classification, and its behavior still challenges the assumptions that underpin much of modern astrophysics. Whether its cause is mundane or extraordinary, the star has already accomplished something rare. It has forced us to confront the fragility of our cosmic explanations. Perhaps Tabby's star is nothing more than an unusual natural phenomenon, or perhaps it represents something far more profound. Either way, it leaves us with an unsettling realization that is difficult to ignore. The universe is not a solved puzzle, but a dynamic system, whose rules are only partially revealed to us, and whose deeper logic may extend beyond the frameworks we have built to understand it. As long as stars like this continue to exist, quietly defying prediction, we are reminded that our place in the cosmos is not one of mastery, but of exploration. We are not standing above the universe with complete knowledge, but moving through it with incomplete maps, interpreting signals that may be far more complex than they appear. Somewhere beyond the reach of our instruments and theories, a star is still refusing to behave as it should, and until we understand why, we must live with the possibility that the universe is not just vast and silent, but subtly active in ways we are only beginning to recognize. The night sky may look familiar, but beneath its apparent stability lies a reality that may be stranger, deeper, and more unsettling than we are prepared to admit.